Alright guys, hello everyone. Hello guys. Alright, so we have a session today on electrochemistry, right? So we'll be discussing, we'll have this particular session, we'll talk about electrochemistry and we'll do a quick revision kind of thing, okay? So we'll be talking about important formulas, okay? And if possible, I'll try to explain some of the concepts also, okay? So important formula. So that's what we are going to basically focus more on. And yeah, so I hope that you guys are watching it live. Okay, so I'll just wait for a few minutes so that others also can join the session. Okay, till the time you guys join and till the time you all come over here, let me just tell you about the Unacademy learning platform. So Unacademy is providing online classes for your CSIR net preparation. So if you guys are interested into that, you can join that. So I am taking classes for chemical sciences CSIR UGC net, and I am teaching basically all the important topics from this particular for this particular category, right? So these are the list of the topics which I am going to cover, like which I have already covered few of them, and few of them are left. Okay, so I'm going to cover important concepts from your organic chemistry except your reaction mechanism. So for reaction mechanism, I'm not taking that class, but some other educator is taking that particular portion. In organic chemistry, I'm completing total, and your physical chemistry also I'm teaching incomplete. Okay, like the complete portion of that. So in that session, what we used to have is complete, like detailed explanation of the topic. All along with that, we also have doubt clearing session, so that whatever doubts anybody is having, he or she can clear up those doubts. All right, after that we also have a quiz or like a mock test kind of thing, so that you can just like analyze that how much you have prepared for that particular topic. And also I give access to the WhatsApp group for those who subscribe to Unacademy using my referral code. So if you want, you can join using the referral code, that is n_huda. So if you take the subscription, you will get 10% discount by using this n_huda as the referral code, and also you will get access to my WhatsApp group. All right, so these are the things which I just wanted to tell you. Good evening, Deepthi. Hi. So now let's shift to the topic, that is electrochemistry. So yeah, we'll have a quick discussion of it. Okay, just based upon important formula and few of the concepts I will explain. Okay, so books which you can follow for this particular topic. I prefer Puri Sharma Pathania as a good book for this particular topic. Apart from that, you can also follow Atkins after following Puri Sharma Pathania. Okay, then in order to solve questions, in order to solve good CSIR and gate level problems, I'll suggest you to go for KL Kapoor. It has it has different volumes of it, so you will get quite good questions in this particular book. Okay, fine. So let's talk about the formula first of all. So electrochemistry starts from the very basic thing, that is from the resistance, conductance, and all those terms. Okay. Hello, Shaukat. Hi. So it starts from there. So resistance is given by this formula, R is equals to rho L upon A. That is the formula to calculate resistance, right? Now conductance is denoted by G, and it has a unit in, like it is inverse of your resistance. Okay, so just like resistance is the property of a material, that how it is, like that property of a material, that it is restricting the flow of electric current through it, right? In the same way, conductance is the property of a material in such a way that it allows the flow of electric current through it. Hello Ajit, I'm good. How are you? So yeah, conductance is the property that it allows electric current to flow through it. So it will be reverse of resistance. Okay, it's just opposite of that. So the formula for conductance is 1 by rho, and it's A by L. Okay, so that is the formula. Now 1 by rho is resistivity. Okay, it's called as resistivity. 1 by rho is represented as a different as a different variable in your electrochemistry. So we call it as specific conductance. Okay, the specific conductance is given by kappa. Okay, that's the Greek letter which shows specific conductance, and this is actually equal to 1 by rho. So now you can substitute all the values over here. So your conductance will be equal to conductance is equals to 1 by rho. So in the place of 1 by rho, I can write down kappa, which is the specific conductance into A by L. Okay. Now A by L has no meaning, but yeah, L by A is called as cell constant. Okay. So we call L by A as cell constant. So what I can write down is G into kappa into cell. G is equals to, it should be G is equals to kappa into cell constant, so into 1 upon cell constant, 1 upon cell constant. Or I can write down that your specific conductivity or kappa is equals to conductance into cell constant. So that comes out to the first formula of your electrochemistry, from where you will at least get a 2-marker question. Okay, so conductivity is equals to conductance into cell constant. Now the next formula is equivalent conductance, which tells you that how much electric current is being transferred by 1 gram equivalent of the solute. Okay, or the solution, 1 gram equivalent of the solution. So that's what your equivalent conductance tells you. So it has a formula kappa into 1000 upon C, where C is the concentration. The next one is Kohl-Ross law. Kohl-Ross law is used to tell you about the molar conductivity. Okay, now you have one more term called as molar conductivity, is given by lambda m. It's lambda. Okay, it's capital lambda. So lambda m is equals to kappa into 1000 upon m, where m is the molarity. Okay, concentration in molarity. Kappa is conductance. Okay, so that's how the formula goes. Kohl-Ross law tells you about the molar conductivity of a particular solution, and lambda naught m is the molar conductivity at infinite dilution. So if you keep on diluting the solution, what is going to happen to the conductivity? So when you dilute a particular solution, the molar conductivity of the solution is going to increase, right? So in that particular way, your Kohl-Ross law tells you about lambda m is equals to lambda naught m minus k. This is k is a constant under root c. C is the concentration. Okay, k is a constant. Okay, it's not kappa. Next is your conductance ratio. It's given by alpha, or it is also called as so conductance ratio. It's given by lambda eq by lambda naught eq, or for molar conductance it can be given by lambda m upon lambda naught m. So it's the molar conductance divided by the molar conductance at infinite dilution. So that's how we calculate conductance ratio. Next is your Ostwald dilution law. Ostwald dilution law is being created in order to find out the molar conductivity of a diluted solution. Okay, so since the formula is for so basically Kohl-Ross law is for the diluted solution. For less diluted solution or for concentrated solution, we use Ostwald dilution law. So it goes like 1 by lambda m is equals to 1 by lambda naught m plus lambda mc by Ka, and Ka is your dissociation constant. Okay, and lambda naught m square. So that's the formula for your for the Ostwald dilution law. The other is transport number. Transport number tells you about that how much. Okay, so when you have, let's say I have a solution, I have put 2 electrodes. This is the positive electrode, this is the negative electrode, and I have solution in which these electrodes are dipped in. So what is going to happen, that the electric current is going to flow inside the solution through ions, right? So there are 2 types of ion, positive ion and negative ion. So how much positive ion is like helping to flow or to make the electric current flow, and how much negative ion is going to help to make the current flow, that is called as the transport numbers of those ions. Okay, so given by T plus and T minus. So the overall value should be equal to 1. T plus T minus should be equal to 1. Okay, the next thing which is going to be very important is the conductor metric titrations. Okay, so I think most of you, those who have physical chemistry in your as the majors in your masters, might have done these experiments. Hello Nana, how are you? Okay, so conductor metric titration tells you about as the titration tells you, in the titration we need to find out an end point. We need to find out that particular point where your solution get neutralized. Okay, so let's say I'm taking strong acid and I'm treating it with a strong base. So what is going to happen, that if I plot conductance versus volume of my base which is being added, so with the more and more base you will add, the less and less conductance it will show. Because let's say, see, you understand it like this. Let's say I have a acid. Okay, so I'll write down like Ha, that's the acid, and I have a base. Okay, so let's say I have BOH, that's the base. So let's say in the starting I have 100 moles of acid and 0 moles of base. So the conductance will be shown by 100 moles of acid. Okay, so that's why the value is quite high. Now if I start adding base now, so I have 100 mole of acid as it is, but yeah, it's 0 over here. Let's say I have added 20 moles of base. So what is going to happen, that 20 moles of this acid will get neutralized. So only 80 moles or 80 percent of your acid will be left out. So conductance will reduce. Conductance will get reduced, and will show you at a certain point over here. Now I am increasing the increasing the volume of my alkali. Let's say I make it 40, and the acid is always like 100. It is fixed. Okay. So now 40 will neutralize the 40 moles of your acid, and what will be left out is the 60 mole. So yeah, again the conductance will decrease. So it will keep on decreasing until you reach a point where all of your acid is going to get neutralized. That will happen when you have, if you, let's say I have taken just a condition. Okay, hello Grace. So I have just taken a condition, so that's why I'm putting 100. So when you put base as 100 moles, so in that case both of them are going to get neutralized. So that is called as the end point. Now if I increase the volume of base, so it's 100 itself, and I'm making it 120, let's say. Okay, I'm giving 120 moles of base. So now 100 is going to neutralize this, but now the 20 mole extra or 20% extra of your alkali is going to create more conductance, right? That is going to give a little higher conductance. That's why you will get a little higher value over here. So you keep on increasing the volume of alkali, now the conductance will increase. So first it decreases and then it increases. You reach at a minimum point, that is called as the end point, when you treat strong acid versus strong base. So that's how we get the curve. So we get a curve in the form of V. When you take a strong acid and weak base, now weak base, you know, it has low dissociation constant, right? So low dissociation constant. Dissociation constant means these are not going to dissociate that easily. So obviously when the acid is there, you are putting base, so it will get neutralized up to end point, and after that end point your base will not get dissociated. So that's why you will not see increase in conductance here. The conductance will remain quite constant. Okay, so why it is not increasing? Because base does not dissociate that easily. That's why. Same goes when you take weak acid and strong base. So in the weak acid, this is for weak acid and strong base. Okay, this curve, the one I have just shown both of them here, but yeah, this curve shows for weak acid and strong base. So you are getting a higher increase in the base because you are taking strong base. So that's why it will dissociate fastly, and that's why you get a higher curve over here. The rest of the curves are not that much changing because it's a weak acid. And when you take weak acid and weak base, in that particular case, you will get two endpoints. Okay, you will reach two endpoints. Why? Because both of them are getting dissociated very slowly. So over here at this particular point, let's say acid got neutralized. Okay, some part of your acid got neutralized but not complete, and at this particular point your complete part of your acid got neutralized. Okay, so that is how you get two endpoints in this particular case. Okay, the next one are your titration curves. What happens in titration curves, that instead of taking conductometric, like in the conductometric titration we took conductance as the property, here we take pH as the property. Okay, now you know the pH of acid is like, pH of acid ranges from your from 0 to 7, right? It's lower than 7, that's what it is. And the pH of your base is from 7 to 14. Okay, that's the range which we know. Now let's say I'm taking a strong acid and a strong base, and remember what you are adding. So I am adding acid. So already what I will be having in my solution, I will be having base in my solution. So obviously the pH of base is higher, right? So that's why the curve will start from a higher pH value. So it will start from a higher pH value, and at a particular point where the titration will happen, at that particular point you will now see, after that particular point your pH will decrease. Why? Because now all the base has got neutralized, only acid is there. So acid will have lower pH. So that's what you are getting over it. This particular point will be called as equivalence point. Okay, so this is a normal curve, but sometimes you will see in books that they also plot a differential curve of this. Okay, so they can also plot differential curve. So if I plot dpH by dV versus volume, in that particular case, instead of having a S kind of curve, I will be having a peak at the equivalence point. Okay, so that's the that is the advantage of using differential curves. If you are good with maths, if you know how differential works, you might have figured it out that why it happens. If you have doubt, you can ask. Okay, why it is happening and all. Yeah. Next is your, when you use strong acid and weak base. Obviously, you have taken weak base. So at the starting the pH will be small, right? It will start from a little lower pH. Earlier it started from, let's say 13 or something. Now it has started from 9 or something. pH will be 9. because it's a weak base. And since you have taken strong acid, so it will end up at a little higher pH. So the pH over here is, let's say, 1. Okay, here also it was 1. You know, so it will end up at a lower pH. So it's all about the pH values. That's it. If you take weak acid and strong base, so for a strong base it will start at higher pH and it will end up not at that much low pH. Okay, so it will end up at, let's say, 4 or 3 pH because you have taken a weak acid. So weak acid will not have a pH value of 1 or 2. It will have a pH value of 4 or 3, right? If you take weak acid and weak base, so both of them will be small. Like it will start from 9 and it will end up at 4 or something. Okay, that's because you have taken weak acid and weak base both. So that is how we plot titration curve. Now, one thing which you have to figure it out, which you have to look upon it very carefully, is that what you are adding. If you are adding base to the solution, in that particular case, what we will say that we already have acid in the solution. So the graph will start from lower pH and it will go to the higher pH. Remember, if you are plotting the graph and you are adding acid, in that case, the graph will start from higher and go to lower. Okay, just like it is happening here in this curve. So you are adding acid, so start from higher, go to the lower. Whereas if you add base, so it will start from lower and it will go to the higher. So that's the difference. Okay, so the way how that S will be plotted, that will be different in both the cases. So yeah, that's how the titration curves work and that's how we plot them. Okay, we'll take some questions also, don't worry about that. Alright, the next formula is on your cell potential. The cell potential tells you about like the complete cell. If you have a particular complete cell, which is like, let's say I have a cell something like this, okay, a galvanic cell in which I have two electrodes, cathode and anode, and I have dipped them in the solution. Let's say I have put zinc in the solution of zinc sulfate and I have put copper, okay, in the solution of copper sulfate. Alright, so what is going to happen, and what you have to attach is, first of all, you have to give a salt bridge and you have to attach it through a voltmeter, and that's how the circuit will be made. So if you look upon this particular cell, you will find out that in the cathode, oxidation will happen. Okay, one side will be cathode and the other side will be anode. Okay, so in the cathode, reduction will happen and in the anode there will be oxidation. So you will see that in this particular half cell, that is in the zinc side, you will see that zinc is actually getting converted into Zn2 plus, and along with that 2 electrons will be given. So with the time, this zinc from this electrode, from this solid electrode, will go into the solution in the ionic form. Obviously in the ionic form it will remain in the solution, you know? So what is happening to zinc? So oxidation is happening to zinc. Okay, and if you look upon this copper side, you will find out that you have copper 2 plus in the solution. So in that particular side, copper 2 plus is actually like it is taking 2 electrons and getting converted into copper. So more and more copper will be deposited on this. So it will become thick and this side will become thin. So here reduction is happening. Okay, reduction is happening on this particular side. So to summarize everything, I have made a very good mnemonic to remember. You can remember this word, lone. Okay, L for left, O for oxidation, A for anode, and N for negative. That means in the cell, your left hand side you will be having oxidation. Okay, so left hand side oxidation is happening, and this side, this particular electrode will be called as anode, and this will have a negative charge. Okay, it will have a negative charge over here. Similarly, the right hand side, you will be having cathode. Okay, you will be having cathode and it will be positive in charge. So that's how you can memorize these things. Now the potential of the cell, the overall EMF of the cell will be given by this formula, that is E cathode minus E anode, or E right minus E left. So that is the formula which can be used to find out the potential of the cell. Gibbs free energy of the cell can be easily calculated by this particular formula. So it's given by delta G is equals to minus NFE of the cell, where F is Faraday constant and it has a value of 96500 as a rough value. Okay, and N is the number of electrons which are given or taken in the particular process. For example, for this particular reaction, the value of N will be 2 because we are giving 2 electrons, because zinc is having plus 2 charge. Okay, the next part is your Nernst equation. The Nernst equation goes like this, that is E is equals to E naught minus 0.059 upon N log reductant divided by oxidant. Okay, so the thing which is getting reduced divided by the thing which is getting oxidized. Okay, the concentration of the thing which is getting reduced divided by the concentration of the thing which is getting oxidized. Okay, or it can be given like this, that is E is equals to E naught minus 0.059 upon N, and you have log product side divided by the concentration of product side divided by the product concentration of the reactant side. Okay, if you know equilibrium, so you might have seen that this is represented by Q. So you can even write down Q over here. Okay, there is one more relation for Nernst equation, which at equilibrium your E of the cell is equals to 0. Okay, so at equilibrium we have E of the cell is equals to 0. Then your E naught of the cell will be given by 0.059 upon N, and it will be log KSP. Okay, so that you have to memorize. KSP is the solubility product. Okay, so it's the solubility product of the salt. So if you are using salt, you can write down KSP. If you are not using salt, if you are just using if you have any other reaction, then it will be log K, that is equilibrium constant. Okay, so that is how this equation goes, the Nernst equation. That is the most important equation from your electrochemistry. And after that you have different equations also, you have Debye and the other equations. Okay, the next one is Faraday's first law of electrolysis. What it says, that the mass of substance altered at any electrode during electrolysis is directly proportional to the quantity of electricity transferred to that particular electrode. Okay, so how much an electrode will get deposited at a particular electrode will be directly proportional to the quantity of electricity that has been transferred to that particular electrode. So M is equals to Z into Q. Z is the charge, and Q over here is the coulomb, like the charge in the coulomb form. Okay, so that will be calculated from the the current value. Okay, Faraday's second law of electrolysis says that when the same quantity of electricity is passed through several electrolytes, the mass of substance deposited are proportional to their respective chemical equivalent or equivalent weight. For example, if I have electrode, let's say I have put different cells. Okay, different cells are here. I'm just drawing a rough figure of them, and I'm connecting them through this. Okay, and I'm giving certain amount of heat to this. I'm trying to do electrolysis. Okay, so when I'm doing electrolysis, so obviously some of the electrode, like some will be getting deposited at their electrode. Okay, the mass will be deposited. Let's say this has mass m1 and this has mass m2. So what it is, the mass of substance deposited is proportional to their, so m1 upon m2 will be equal to the equivalent weight of first divided by the equivalent weight of second. So it will be proportional to the equivalent weight of that particular chemical substance which has been used. So that's what your Faraday's second law tells you. Now you can relate your thermodynamic constants, thermodynamic variables basically, with your electrochemistry. Okay. For example, you can relate Gibbs free energy over here. You have this equation called as Gibbs to Hem equation. Right? Sorry, Gibbs-Helmholtz equation. So this is called as Gibbs-Helmholtz equation. So Gibbs-Helmholtz equation says that delta G is equals to delta H plus T del delta G by del T at constant P. So we know that delta G is equals to NFE, right? And that too with a negative sign. You can substitute it over here, and when you form, the equation changes to this. That is, E of the cell is equals to minus delta H upon RT plus T del E of the cell by del T at constant P. The next term which we have to discuss is the ionic strength. Ionic strength tells you that how in a particular solution, when you have, let's say, a particular salt which has been dissolved in the particular solution, so in that way you will be having different charges on the salt, right? So how much a particular ion is constituting, or it's helping for the electric current to flow in the particular solution gives like that you can calculate through your ionic strength. Okay, so ionic strength tells you about the strength of the ionic solution, you can say for a very layman language like that. So ionic strength is equals to half m1 z1 square plus m2 z2 square plus m3 z2 square, and so on and so forth. It depends upon how much things you are going to add. Now you can replace this m with the concentration as well. So you can have this formula, that is half C1 Z1 square plus C2 Z2 square plus C3 Z3 square, and so on. Okay, so Z1, Z2, Z3 are different different species which are being dissolved in that particular solution. Okay, the next is mean activity coefficient, mean ionic activity coefficient given by gamma. It has a formula that is log gamma plus minus is equals to minus a, and you have z plus z minus I under root I, or I to the power 1 by 2. Over here a is a constant, z plus and z minus are the respective charges on cation and anion, and I is your ionic strength. So you can put that and you can calculate mean activity coefficient. The next thing is Debye-Hückel limiting law. Debye-Hückel limiting law basically tells you that what actually happens, what is the condition for this, is that let's say I have put a positive charged species in the solution. Okay, so what is going to happen, that inside that solution whatever negative charges will be there, they are going to come near to that. Okay, they are going to come and they are going to actually surround this positive charge. They are going to make a layer around it. Similarly, then a positive charge will come and it will make a layer around that negative charge. Okay, so basically there will be a length up to which, or a distance up to which this particular charge species, the positive charge species, will have its influence, okay, over the other particles in the solution. So this particular length, this length is called, denoted by lambda d and called as Debye length. So Debye length is the length, or is the distance up to which the attraction force or the force, hello Mani, hi. So lambda d is the Debye length. It's the distance from that particular charged species up to which the influence of that can be seen on the other ionic species in the solution. So it's given by 1 by kappa, and that's equals to epsilon naught epsilon r kbt divided by 2 nae square into 1 by I and whole to the power under root, or whole of the thing is in under root. So you have to memorize this formula. And also one thing which you have to keep in mind is that your Debye length depends upon what? So it's actually it's actually proportional to, you can say that, temperature and inductive temperature and your ionic strength. Okay, hi Kranti, hello. So it depends upon both the things. It directly depends upon the temperature, whereas it inversely depends upon the ionic strength. Okay, so that's how you can understand that if you have a solution which has more ionic strength, its Debye length will be small, and if you increase the temperature, your Debye length will increase. So that's how we can you can understand, and you can summarize all these things, whatever the important formula were there in the Debye-Hückel limiting law. Now there are many things which I have not included because I have just been allowed to teach for 30 minutes, and in 30 minutes it's impossible to teach electrochemistry or any topic from physical chemistry. So that's why I have just taken the only important points, just to make sure that the things get revised to you. Okay, hello gaming family, hi. So yeah, so that's why we are just doing it in a way so that we just go through the important things. All right. So the next thing is ionic strength of electrolytic solution. It's given by this formula, I already told you. So you can write down that particular formula for the ionic strength. You can write it like this also, that is sigma half Ci Zi square, where C is the concentration of the ion and Z is the charge of the ion. Now you can have two kinds of you can have two kinds of cell. One is with liquid junction potential and the other one without liquid junction potential. See, actually what happens, let's say I have a cell and I have separated it along with a porous membrane. This is a porous membrane, and I have two electrodes, one electrode here and the other one over here. Let's say this is anode and this is cathode. So what will happen, that after some time my more number of positive charges will be there in this particular side, and there will be more number of negative charges which will be there on this particular side. So these positive charges will try to go to this particular side in order to get neutralized with this negative charge. So what is going to happen, that at this particular porous membrane there will be lot of charges which will develop. Okay, those positive charges will develop this side, negative charges will develop this side, basically creating a junction kind of thing. Okay, a potential junction. So that is called as a cell with liquid junction. Okay, liquid junction potential. So we call it cell with liquid junction potential. And if you put a salt bridge over here, so this particular charges will get automatically neutralized, and that will be without liquid junction potential. So with liquid junction potential and without liquid junction potential are these two cases. So in with liquid junction potential we have this particular formula, that is minus 2 T minus. T minus is the transport number of the anion. Okay, RT by F ln A plus minus 1 by A plus minus 2. So it is the activity of the one side and this is the activity of the other side. Okay, these are the two different activity values. Okay, so activity you can calculate from here, right? If you know the mean ionic activity coefficient, you can calculate the activity as well. Yeah, the next thing is E of your without liquid junction potential. So over there this transport number will not be there. We'll just have minus RT upon F ln A1 by A2. Okay, so this is without liquid junction potential. So that's it. I think that's all for this session. I have just taken all the important things from this particular topic and I just try to like give you a very short and precise definition and important formula so that before going for exam you can just revise everything from here itself, right? And before ending the session, I would just like to tell you once again that Unacademy is providing live classes for your preparation of CSIR net exam. 2 new courses are going to come and those will be revision courses, okay, revision courses and your PYQ course. So for these two particular courses, what is going to happen that if you join and if you enroll for these courses, you will get a good revision of the topic as well as if you practice PYQs. Yeah, it is going to help you for the upcoming exam. Okay, so you can enroll yourself into the Unacademy Plus platform and you can just take advantage of these things. So to join that, you just have to take subscription using my referral code, that is n_huda, and with that you will get 10% discount and also access to my WhatsApp group. Okay, so that's all guys from my side. Thank you so much for joining live in the session. We'll be live again I think in the next week maybe, okay, with a new topic. So till then, have a great day. Bye. Yeah, one more thing before ending the class is if you like this particular video, give it a like. Okay, okay, gaming family, I'll try to give the PDF. Okay, I'll try to attach the PDF with that description over here. So yeah, Rasendra, yes, I'm making videos on YouTube. You can check out my channel. Okay, the channel name is All About Chemistry. So you can check my channel over there. So I make videos over there. Yeah, so if you have not subscribed to this particular channel, you can subscribe to this. If you like the video, give it a like, and that's all from my side. Okay, so thank you so much for watching. See you guys.